Got a nice group here. We'll give them all a chance, so we won't start early. All right, but we will stay right on time. So welcome back, everybody. It's a pleasure to turn the session over to Barbara Nimershiem from Franklin Marshall College. You can see her title on the screen, so take it away, Barbara.
Thank you. I want to start by acknowledging that many of us are gathered on homeland of Native peoples. I'm speaking from the land of the Susquehannock. It's also been home to the Lenape, the Nanticoke, the Piscataway, Seneca and Haudenosaunee Confederacy, Shawnee, and many others. I also want to acknowledge that my institution's presence on these lands is a direct legacy of settler colonialism. And I want to thank the organizers for the opportunity to speak, and all of you for coming. If you have a question, please unmute and shout it out, because I don't think I'm going to be able to see it any other way. So today I'm going to be talking about triangulating a family of knot and link complements in the 3-sphere. The triangulations are going to be by ideal tetrahedra, which means that their vertices are removed. Sometimes we're going to depict these tetrahedra as flattened into squares, or maybe half discs. And sometimes we would take like this edge, this 0,3 edge, send a point to infinity and show the tetrahedron as flattened into the upper half space. So all three of these are ways that we're going to be thinking about the tetrahedra. The knot and link complements that I want to triangulate, I want to show that they're hyperbolic, that they admit a complete hyperbolic structure. So probably a better way to draw my tetrahedra would be that, but even a better way would be this, because what I'm really gonna want to focus on is to have positively oriented tetrahedra. So if we put one vertex at 0, one at 1, one out at infinity, then the fourth vertex would be in the upper half space, would have a positive imaginary coordinate. If such a hyperbolic tetrahedra is determined by 3 angles, because the opposite edges in the tetrahedra have the same angle. So basically there's an angle at those 2 edges, the same angle at those 2, the same angle, the same angle at those 2. And if these edges actually tell you the volume also of that hyperbolic tetrahedron. And if we can assign angles to each of the edges in a triangulation, and if we can do it in such a way that when we glue up the faces of the tetrahedra, we get a complete hyperbolic manifold, then we have a geometric triangulation. And it's, I think, surprising that while all non-compact finite volume hyperbolic 3 manifolds have topological triangulations, it's unknown in general whether they all have geometric triangulations. So it's not known whether all of them have geometric triangulations. Epstein and Penner showed that kind of the worst case would be that some tetrahedra might have to be flat in order to achieve a given topological triangulation. But given that, there still are some infinite families of hyperbolic 3 manifolds that are known to have geometric triangulations. Gueritaud showed that punctured torus bundles, 4 punctured sphere bundles have geometric triangulations. Futer did it for 2-bridge knots and link complements. Ham and Purcell have shown that certain Dane fillings of fully augmented 2-bridge knots and links have geometric triangulations. And today I'm going to show you another infinite family with geometric triangulations. It's a tiny piece of the big world of hyperbolic braids. So a closed braid is hyperbolic if it's complement in the 3-sphere admits a complete hyperbolic structure. And we actually know which 3 braids are hyperbolic, which ones have that complete structure on their complement. And they're the ones that have the sort of usual Schreier form here. Let me just remind you, in the braid group on 3 strands is generated by σ1, which is to take the first strand over the second, and σ2, which is to take the second strand over the first. And we have the relation in the braid group that σ1, σ2, σ1 is the same as σ2, σ1, σ2. And when you take this element and square it, that's the C that's in the Schreier form. So let me say C is going to be, and C is a full twist. And it also commutes with every element, so it's central. And here's an example. You can see that I have 2 full twists here, σ1 to the 4th, σ2 to the -3, or sigma. The braids that I want to look at today, I'm actually just going to stop right with 1 σ2 to the -1. And what we really care about are closures of these braids. So let me just close it up to remind you that that's what we're doing. So we're looking at closures of these braids. And closures of these braids, they're all, so this is, we're going to look at C2, σ1 to the P, σ2 inverse, and their closures are pretzels. Every one of them is a and I can't spell pretzel right now. There we go. Everyone's a pretzel. They're also examples of Berman and Kaufman's T-links. And in fact, if you have a T-link on 3 strands that's hyperbolic, it'll have the form C to the K, σ1 to the P, σ2 inverse. So this is a subclass of all the hyperbolic T-links on 3 strands. And it's good enough to focus our attention just on the places where we have the half twist, just on this product region. Let me just blow that up. Yeah, so that is good. It's good enough to focus our attention there for doing the triangulation. And when we do that, we're going to get a triangulation that's an analog of Sakuma and Week's triangulation of 2 bridge knots and links. You might be worried about missing the full twists if we do this. Remember, we had 2 full twists. What is true, and I could say more about it at the end if people wanted, I have pictures, extra slides with it on there, but I can triangulate the top of the product region and identify those triangles in such a way that they will twist up to make a full twist. And you can do that on the top. Of course, you can do the same thing on the bottom. And so then you can introduce those twists by doing just the identifications of the triangulation. And so we can just focus on the product region. Instead of looking at this product region, what I'm actually going to do is push this half twist through the full twist at the bottom until it comes out on the other side. And this is the product region that I'm going to look at to triangulate. And so I'll end up looking at where we have σ1 to the P, and then I'm going to call this σ4 to the -1, because the 4th strand is going under the 5th strand. So I'm going to show you a picture of this triangulation. It has a lot going on in it. So let me try to focus your attention on different pieces of it. In the middle, basically this is 3 different versions of the triangulation. The triangulation in the case that P equals 1 because we just have 1 sigma-1. So in the middle, you'll see these tetrahedra. 1, 2, 3, 4, 5, 6 tetrahedra. And then I've drawn them flat over here. So this is a collection of 6 tetrahedra. The picture on the left shows you how they fit in the braid complement. And so the way you want to think about it is, maybe I'll just look at this bottom one. So this has 2 tetrahedra, one in the front of the page and one in the back of the page. And I've kind of blown it up to cover this region right here. So you can see the top faces are on the top layer of that region and the bottom faces are on the bottom layer of that region. And it's the same thing. The 2 in the middle cover this region, and the top one of them covers that and one of them covers the other. So the top 2 tetrahedra share the 0 to 5 face. So for example, this is the orange 0 to 5 face on the left, and this is the orange 0 to 5 face. And those 2 faces are identified between the 2. Excuse me. Here's some other identifications. The 2, 3, 4 triangle here, which you can see on the left-hand side, it just goes down. There's no 2, 3, 4 triangle in this picture. So it's not there, it's not there, it just keeps going down. But if you watch as it goes down, when it gets to here, one of the vertices will go around the twist. And so this 2, 3, 4 triangle would go to a 2, 4, 5 triangle. And so the 2, 3, 5 triangle in the top layer is going to get identified to the 2, 4, to the 2, 4, 5 triangle right there. And we could follow, maybe I'll just follow one more. I'll follow the blue one. So the 1, 2, 5 triangle, which is the blue one in the in this picture, the 1 is going to twist over to here. You'll get that triangle. There's no corresponding triangle there. Still no corresponding triangle. We keep pushing it down. There's still no corresponding triangle. Still no corresponding triangle. But one of the identifications from doing the full twist on the bottom will take this triangle, the 0, 2, 5, 1 in the back, to the 0, 3, 5, 1 in the front. And so the 1, 2, 5 will get identified to the 0, 3, 5 on the bottom there. So you can cover the whole complement by pushing those triangles through. We just don't have time to do that. If you want, what we really want to do though is we want to triangulate ones with more half twists, more sigma-1 half twists. And so what you can do is you can just insert more layers. And so that's here I inserted those that pair to cover more half twists. The next thing I did is simplified this triangulation with Pachner moves. Again, that's something else I could say more about at the end. I used a 3-2 Pachner move and then a 2-0 Pachner move and got a very nice triangulation. And you can do this in general. So this is actually the triangulation for any P. So this is a triangulation for sigma-1 to the P. Sigma-4 inverse, which we don't even need in this picture. And you can see almost all of these tetrahedra in the knot complement. So there's 2p of them right here that appear in the knot complement the way I was showing you earlier. And then there's one extra tetrahedron that doesn't appear in the complement. It's kind of stretched out and twisted around, and it's introduced by that 3-2 Pachner move. these dashed arrows show you how to identify the faces. So for example, this 1, 2, 5 face in W0 prime is this face right here. It gets twisted around to be the 0, 2, 5 face on the top of W1 prime, whereas the other face on the bottom, the 0, 1, 5, 1, 5 face, gets twisted all the way around to the front to be the 0, 1, 5 face in the front. So this face right here. And so all those identifications just keep going down, down, down. And so the bottom of the pairs on top get identified to the tops of the next ones. And so on, the top of this one and the bottom of this one end up getting identified. And there's some that are missing things to identify, and they get identified to the S. If you're familiar with veering triangulations, you may notice that I colored this to indicate that these triangulations are in fact veering, and that's going to be really helpful to us. So sort of a short definition is you can color all the vertical ones red, and you can color all the horizontal edges blue, and the diagonal edges you can color either red or blue, and just in a consistent way that goes up with the triangulation. And the reason that veering is going to help us is it actually will help to show that the complement is geometric, so that this triangulation is geometric. And to do that, we'll use the Casson-Rivin program, and the Casson-Rivin program is based on the Casson-Rivin theorem, which is I cannot recommend this paper enough. The paper is called From Angled Triangulations to Hyperbolic Structures. And it's from 2011. And they just give a very beautiful exposition of the Casson-Rivin theorem, which was proved independently by Casson and Rivin, and then Futer and Gueritaud explain how you can apply it in general to get this outcome of geometric triangulations. So looking at the theorem a little bit, you start with an orientable 3-manifold whose boundary consists of tori, which is what we have because we have not or linked complements, and an ideal triangulation of it, which we have. And then in that context, a point in the space of positive angle structures. So the space of positive angle structures is the space that assigns angles to the edges of the tetrahedra in your triangulation. And a point in there is going to correspond to a complete hyperbolic metric on the interior of M, which is exactly what we want, if and only if that point is a critical point of the volume functional. And the volume functional just says, okay, add up all the volumes of the tetrahedra that you get by using those angles. And so this lays out a plan. Basically, if you can show that you have positive angle structures, then the closure of positive angle structures is a compact space. And so the volume functional is going to achieve its the critical point will be a maximum. The volume functional will achieve its maximum. And then if you can make some argument that that maximum doesn't happen on the boundary, then you're done. You have a geometric triangulation. So let me just reiterate that. So the steps of the program are, you want to show that the space of positive angle structures on a triangulation isn't empty. And then of course that tells you that there is a place where the volume functional achieves its maximum. And then you provide some argument of why that maximum can't happen on the boundary, and then you have your geometric triangulation. And so all we really need to do are those 2 bullet points. And the reason I wanted to have a veering triangulation is because Hodgson showed that veering implies there exists a positive angle structure. So the fact that triangulation is varying means we have that positive angle structure. So we're in the position of being able to apply the Casson-Rivin program. And then you really don't want to see this, but this one, this proof is just basically by brute force. It uses the edge relations and some symmetry of the space of angle structures. And then, so from there, we can just show that the maximum can't happen on the boundary, has to happen on the interior. And so if the maximum happens on the interior, that point, that certain assignment of angle structures is a complete hyperbolic structure. And we have geometric triangulation. So thank you very much.
All right, thank you. Questions for our speaker? Feel free to just jump in with a question.
I'll ask the obvious question, Barbara, which is, do you think this extends to other 3-braids? What, how constrained are these methods?
So I can add a full twist. So kind of moving along in the direction of hyperbolic T-links on 3 strands, but I can do that with the triangulation, but it's not varying, it's close. So maybe there's still a way to apply the Casson-Rivin program. I can definitely do. Oops, sorry, I'm doing the wrong thing. I can definitely do this, get something that's varying. It's going to take a little bit more arguments to get that the maximum doesn't appear on the boundary. And I've made a little bit similarly, kind of a little bit of progress on the more general thing of concatenating more sigma-1s and sigma-2 inverses. But I don't know. It gets complicated fast. So I'm not sure it's the best way to go.
Okay, other questions? Okay, if not, let's thank our speaker one more time.